Okay, so what we were doing in our previous class was we were learning this phase 2 software. So what problem we had was we were discussing about a tunnel of radius. Anybody remember or maybe can tell me what was the radius of this tunnel? No. Okay, this was a 5 meter radius tunnel. And then we said, like that we have two cases. One is with sigma v equal to 19.5 MPa. We have sigma h here, which is in case one. We have 5.85 MPa, and in case two, we have 39 MPa. Okay, just a second, students. Yeah, so what I was saying is, like this, we had two cases. So where we have some stresses from the top and from the sides, right? And we were looking at what is happening to this boundary of the tunnel. So at 2 points, one is P1 and another is P2. So what are the stresses that is going on here? So and we solved it. I think you guys have submitted this thing also. So what we were looking here was sigma theta at the boundary of the tunnel at 2 point P1 and P2, and for the two cases. So we have case 1 and case 2, and what we are doing here is we are comparing the Gauss equation with our FEM result. So what is the Gauss equation is giving for this thing and this thing, and what is FEM is giving. Okay, so what for the first case, what we got was 52.65 minus 1.95, and then Cox equation is giving again 19.5, and this is 97.5. Okay, so we learned up to here, and anybody has any question up to here? Anyone? No? Okay. So then we created the model, right? Like the whole thing in phase 2. Please see the previous video how to create it, and one small change I made here, and that was how many segments are there around the boundary. I increased from 40 in our previous case to 100 in this case. Okay, so we have finer we call it elements near the boundary here. Okay, and then you can click this compute. Okay, let me take it this thing. So if you see, can you see this compute button on the top? Anyone?
Yes, sir.
Okay. So then once your model is created in your previous case, then you just click this compute button. Okay, so this one. this one here. So if you click it, you know, the problem will be solved for us. And then there is something called interpret. Okay, let me take a screenshot of this. Yeah. So then click this interpret thing. So this one here. You can see this, right? So click this one. So let's do that. So if we click it, you know, it will show us the results. Okay, I can remove it. Okay, done. So yeah, so what it is, like we have now two stages. One is the in situ stage here, like the first stage one, and second thing is the tunnel is excavated. Okay, so and in the left side here you can see this thing. It says the contour values. Let me change a few things here. Go to contour option and fill with lines. Okay, so what does this mean is, let's say this green and the blue one. So where is that boundary? This green and blue boundary is somewhere here, right? Can you see this here? This one here. Let me take a screenshot of this. Okay, so let's see this. What I'm saying is, what it says is, it tells us what is the major principal stress around the opening. So this is the sigma 1 values. We already know what is our sigma 1 and principal stresses, right? So in our hook around failure criterion, so where we plot our sigma 1 and this is sigma 3. Okay, so this sigma 1 is a sigma 1. This is the one we are talking here. Now, if you see this color and this color, can anybody tell me what is that, you know, which distinguish between these two colors? What is the value in here which corresponds, you know, to these two colors? Anyone? Guys, please let me know if you have some, you know, problem understanding anywhere.
Sir, blue and green.
Sir, 18.
Yeah, this color here. So see, we have, you know, can you see this 12 here and 15 here?
Yes,
Yes.
sir.
So what it is trying to say is, you know, like the value of the major principal stress is 12 here, 12 MPa, and in here this is 15. So if you want to know your principal stresses between these two lines, you can calculate, you know, interpolate like what will be the value here. Okay, because for this color, you can see from here it is changing from 12 to 15. Is this clear? How to understand what it is saying here? So if
Yes.
you want to know, like, what is the, if I ask you what is the, you know, sigma 1 value here, can you tell me? What is the, anybody? What is the sigma 1 value here? Sorry?
18. Sir, it's
18?
15. For its
Yeah, it's 15 itself, right? Like if you take any point around, you know, this line, this is 15 MPa line. Okay. or this is, I'm sorry, like maybe this is the color for 15 and this is 12.
So that
Okay.
is green one. So 18 should be there. No?
Yeah, 18, yes, 12 and 15 and 15 to 18. Okay, so all these points, they are 18 MPa. So this, after this calculation, it tells us, if we increase the, number of contours here, it will tell us what is the, the principal stresses around the opening. Let me quickly show you that thing. This is pretty interesting kind of software. So if you click this one here, it says add material query. Okay, and if you put this thing here, click the first point, okay, and click another point here, and just press enter. It will ask at how many places you want these values. So let's say make it 20 places. So at different 20 locations, it will tell us the value. See, this is the 18 contour, right? Okay, so this is exactly what it is doing. And this is close to 15 because it's a little bit above that point, like this line. So this is exactly 15. Okay, so and it is increasing from 15 to 18. Is this clear? So this software actually tells us at different locations, how the principal stresses are changing. Sounds good? Anybody has any question? Anyone? Are you guys there? Yes, no, but
Yes, sir. Understood.
understood.
Yes, sir. Yes, sir.
Now
Yes, sir.
let's put it here. So these are the sigma 1 values. Now let's say I want to know whether this point is within the safe zone or not. What we discussed in our class is like we need to go to our failure envelope where the sigma 1 and sigma 3 is plotted, and we need to see where this point is here or here. Okay, so if this point is below this curve, this is a safe point, and this is a failed point. We have already discussed about this. Okay, now let's see the same thing in here. Okay, so this is 17.14, and if you see here, and if instead of the sigma 1, if I make it sigma 3, so see the same value has been changed. So but we need to note it down. Let's say exactly, maybe it was somewhere here, right? Or let's see this. And so from the point, it was 17.34. 1, 2, 3, 4, 5, 6 point. Okay, from the top. So if you see, or maybe let's take a screenshot of this. So this sigma 3 value. So yeah, if I plot it here or put it here, so if you see, this is the first, second, third, fourth, fifth, sixth, 7 point we are looking at 17.14. So the 7 point 1, 2, 3, 4, 5, 6, 7. So what is this value? Can anybody tell me? Can you read this?
6.38.
38.
6.38,
6.38,
right?
sir.
Yes, 6.38. So what is this? If I put both the things together, what is the sigma 3 and sigma 1? So 6.38 set a set of this sigma 3 and sigma 1, this is 6.38 and 17.14 or something. Okay. So if you know your sigma 1 and sigma 3 value, and you could test the rock in the laboratory, like, okay, this is my, and get your failure envelope using your, either Moore Coulomb or Book Brown, you can put this point here and see if the point is here and if the point is, or the point is here. Okay, so if the point is here, you don't have to design anything. You don't need to design any support system. Okay, but if the point is above this thing, what you need to do is, you need to provide some support system so that the, the factor, like the point will, after excavation, the point will go below this line. So that is the main task when we design, any underground excavation. Is this clear? It is clear, like why we do this FEM analysis and how it is useful.
Yes, sir.
Okay, so yeah, so let's go back to the this thing here, and just to check some values. So let's say when in situ condition, all the values were 5.85, which is our horizontal stress. You can see this is our horizontal stress. So you can see there are so many things here. Let me take a screenshot of this. So yeah, so what the software does is it calculates, when you give some input, it calculates different things like our sigma 3, sigma 1, sigma z, which is the stresses in perpendicular to this plane, right? What is the stresses, and so many things like, like the horizontal, and but the most important things are, this sigma 1, sigma 3. And you can go through this one Mrs. stresses, like this is not, it's out of our syllabus. It's advanced of that we are not discussing here. Maybe the horizontal displacement, how it is doing, what is the vertical displacement, what is the total displacement, and what is the strength factor. This strength factor is your factor of safety at different locations. Okay, so this is very important. And this is sigma xx. What is the vertical stress? Sorry, this is sigma h, and this is our sigma v. Okay, so these things are very important. If you click this, the triangle here, the drop down menu will come and you can select the value and you can see the different things. Let's do that. So if you see the sigma xx in horizontal direction, what is the stress? See, this is a 5.85 that we applied to the model. So if you see here, in the first case, what we applied 5.85 MPa. So that is the value it is saying, showing to us. In all the points, we have 5.8 MPa of horizontal stress. Okay, so in here, that is why this is 5.85. So these values, just remember, these values are in MPa. Okay, because in settings, we put the values should be in MPa. Like, so what is the vertical stress? Can anybody tell me what was the vertical stress we applied? Come on. What was the vertical stress we applied to the model?
So 19.5.
Yeah, 19.5 MPa, right? So that is why we are getting this 19.5 throughout the model. Okay, means you applied the boundary condition correctly. This is what it means. Okay, so let's see some other things. Let's say the displacement. When you apply this boundary condition, you can see how the tunnel boundary is displacing. Okay, so if you see the total displacement contour here, you can see this is 1.32 into 10 to the power minus 2 meter. Okay, so this is the displacement. Let's take a screenshot of this. And put it here. Sorry. Put it here. So the displacement, which is the vertical displacement, it is 1.32 into 10 to the power minus 2. In centimeter, what will be the value? Can anybody tell me what in centimeter what is the value?
So this is in meter.
Yes, this is in meter.
732 centimeter.
No, into 10 to the power minus 2 is there, right? So 1.32 centimeter. So from here you can find out that like that the displacement in here is 1.32 centimeter. And why we have a like this arrows, they are saying that at what point what is the displacement. And because we applied some 19.5 from the top and 5.85 from the side, we expect that okay, because this stresses is more, that this point will displace more, right? And this is exactly what it is doing. And this point has almost zero displacement. Okay, is this clear? So these are the displacement contours. Okay, so is anybody has any question? Please ask me. Okay, so now our main, the point was to compare our this Course equation and APM, whether it is behaving correctly or maybe giving us the correct result or not, right? So for that, what we are going to do is we are looking at the stresses, here. Yeah, so we are looking at the stresses at this point. Let's zoom it out a little bit, take out this displacement. So we are looking at, the stresses at this point and in here, the middle point, right? So if I want to get the tangential stress at P1, which is this point here, can you tell me which contour I need to see? Did you understand my question? So what I'm trying to say is, we have this tunnel here. At point P1, I want to see what is the tangential stress, and at point P2, I want to see what is the tangential stress. So at P1, can you tell me what contour I will look for to know what is the tangential stress? Anyone? Guys, are you there?
Yes, sir.
So can you tell me what contour I'm going to see? So in the drop down menu, what stresses I'll be looking for, or maybe do you think that if I plot my horizontal displacement, then I can see what is the stresses here? No, right? So you need to see the stress values. What is the stress value? Can anybody tell me which stress I need to see? Is the question clear to you?
Sir, like sigma 1, sigma 3.
Here, see, this is vertical stress that is acting, right?
So then
So
sigma.
our tangential stress here is the vertical component of the stress. Okay. So to see the stresses here, I need to, get my sigma V plot, sigma V contour. If I want to know my tangential stress here, which contour I need to see here in P2?
Horizontal.
Yeah, horizontal stress, right? Like what is the horizontal stress? Because if I see the vertical stress here, this will be 0, right? You just see that. So let's take this thing. Yeah. So there is, you just right click on this and you just go for this query boundary. So let me copy this so that you remember this. So just go and click that query boundary. So here, what you need to do is you just right click and query boundary. And on the excavation boundary and click OK. So see, if I see my vertical stress, let's see how much it is coming at the middle point. Can you tell me the value? Anybody?
Said 5.263.
Into 10 to the power 1, right? So, just a second, I'm getting a call from Professor Mandal. You just think about it, okay? Yeah, so see, like at this point, which is our, the P1 point, the value is 52.63 into 10 to the power 1. So let me take this value and this value. Put it here. So this is 62 point or 52.63, right? So this value equal to sigma V equal to your sigma theta equal to 52.63 ampere. Is this clear? Similarly, I told you that, if you want to know the tangential stress here, that should be your horizontal stress, right? So in here, this is, you can see the value is minus 1.702 into 10 to the power minus 10 to the power 0. So if you just click this one here, you need to understand, otherwise you cannot solve your project. So please let me know, just to, like I'm just helping you to solve your, what is this called, your project. So if you're not understanding anything, just let me know. Okay, so this value is minus. Minus means what? Can you tell me what is this minus means? Negative means?
The tensile.
Yeah, this is means tensile. And what is the value in ampere?
Sir, 1.702.
So sigma h equal to sigma theta equal to minus 1.72. Just remember this value, okay, in ampere. 52.63 and 1.7. Yeah, so this is 52.63 and minus 1.72. See, this is super close to that value, right? Like maybe so close. Okay, so there is a minor difference between here. And that difference, it depends how fine your zones are. Okay, so this is a top point, and you can see this point and this point. The like this is more than 150 centimeter or 158 centimeter. So if you make this more and more fine, this value like the FEM result will be close to that concentration. Okay, is this clear?
Yes, sir.
Okay, so what I'm going to do is, what I've done is I have put these softwares in Google Drive. Okay, so you please download it